Hello, Apurva sir. So,
Sarfraz sir,
yes. So, are we waiting for some more participants?
no, time is ripe. You can start now, I think.
Okay, fine. So, I shall start then. Let me share. So, is it visible, this tool?
Yes.
Okay, so I would just show one example for getting the parasitic capacitance. So, someone asked yesterday that how we can find out the parasitic capacitance. So, so for finding out the parasitic capacitances, like we need to run this one. So basically what we do is that we find the operating points. For suppose say for this inverter I want to know the parasitics of PMOS and NMOS, so I can use this dot op. Okay, so this operating point, we can run this one, and we can find it out. So there is no command for finding out the parasitic capacitances. So that is why we need to find out the operating points. So once we get the operating points, we can view inside this one. So we can view the internal capacitance of PMOS and NMOS. So, and in this case, as in the last class we have seen, okay, so in the last session we have used 180 nanometer. Now I have taken one example. I have taken one 45 nanometer this technology from the PTM library file. So this also I can I can show that for what will be the output for a 45 nanometer technology. So here I can take this VDD. So this VDD, in the PTM file it is written that the optimal or typical is 1 volt. So I will be taking 1 volt as the VDD. So let me just rewrite this one as VDD. So VDD I'm taking 1 volt for this one, and let me just run this particular simulation. So since I am considering only the DC operating points, so I'm just finding out the operating point. So I'll just run this one, and you can see the different operating points. So what is the ID, current, and all those things. So details we can get it from here. Now we need to know about the parasitics. So what we'll do is that we'll close this window, then we'll go to view, and we'll click on spice error log. So once we click on this one, the details of the MOSFET model. Okay, so the details will be shown over here. So as you can see, the details are shown over here. So ID, current, VDS, VTH, VDSAT. So what will the VTH value? What will the VDSAT value? What will the transconductance? So GM, GDS, GMB, then CBD and CBS. So two model parameters are there here. So CBD and CBS. So that is why it is showing only these two. But it can differ. These values or these model parameters will vary for different model files. So since I'm using this 45 nanometer from the PTM, so they only are having these, like it is calculating only these values. But we can also calculate it for the other values also, like CGS, CGD. So these values also we can have, but for that we need some other model file. Like by using this model file we cannot find out. So that is why we need to find a separate model file where we can find out the CGD and CDS values. So this is how we can find out the parasitic capacitances. And here also we can find out the GM and GDS. So by knowing the GDS value, okay, so we can just size the transistor also, like according to our calculation. Suppose we want to consider or we want to design a particular inverter. So when we design a particular inverter, so we actually simulate this one and find out the propagation delay. And the propagation delay, so we can calculate, like this we will consider as a resistor, like PMOS resistor, and this one is NMOS resistor. So when we consider this one as resistor, so then we calculate that this is a resistor, here is a capacitor. So how much charge is being, like how much time it is taking for discharging the capacitor, and for in case of the PMOS, so we see that how much time it is taking to charge a particular capacitor. Now these two times, okay, we'll take the average, which will give us the propagation delay also. And by using the formula of tau, okay, so tau is equal to 0.69 RC. So I'll just write it down. So tau is equal to 0.69 into RC. So this RC value, so when we simulate this one, so we already know the tau value, or we can just fix a tau value, that what is the value of tau that we want, and capacitance value we already know. So according to that, we can fix the resistor value. Now we can size the particular transistor to give us the same resistance value. So this is equal to the RDS value, which is equal to 1 upon GDS. So this value, so R is actually equal to RDS, and this is equal to 1 divided by GDS. So when we simulate this one, so we already know the GDS value, so we can we can size the transistor according to this particular value, and we can get the required tau value that we want. So these are some of the examples, okay, and I also wanted to show the AC analysis, okay. So one more, so related to this parasitic capacitances, and one more was there, that is about the Monte Carlo analysis. So I will also show you that particular example as well, that how we do the Monte Carlo analysis. So for Monte Carlo analysis, actually there is a inbuilt function, okay. So we can basically use the inbuilt function of Monte Carlo analysis, or we can use another function, okay. So suppose I want to do a Monte Carlo analysis for these transistors, so I'm taking the same size of these transistors. Just to show the difference between these two, I've taken two inverters of same size, and here I have, just in place of the width, I have placed the Monte Carlo value, okay. So how do we do that? So here I have written here, so Monte Carlo function, which is an inbuilt function of a LT spice, so it is written like this, MC, and in here you have to place the nominal value, okay, and here the tolerance, how much tolerance you want, 5%, 10%, 20%. So we can give any tolerance value over here, and it will do the Monte Carlo analysis using that tolerance value. Now we can also give the tolerance according to our needs. So here you can put this particular formula also, MC, okay, that Monte Carlo function, and here any nominal value that we want, and the remaining part, okay. So this remaining part, that is 20 e to the minus 3 and 0.4 e to the minus of 6. So these values, actually this particular tolerance value, we can fix from either model parameters, or like this equation we can just directly put over here. So if we use this particular parameter, then also we can get a different value of this particular PMOS. Now let me just run this one and show you the difference. So if we consider this output, so output 1 means the output of this particular transistor, this particular inverter, and output 2 is the output for this particular transistor. Now if you will zoom into this particular portion, you can see the difference over here. So there is a difference. So when I am putting the Monte Carlo and I am giving some tolerance, so in this one, in PMOS, I am giving a tolerance of 5. Now if I make it 0, okay, suppose I am giving no tolerance in this one, so I am just giving it 0 and I am running this one. So now if you zoom it, you will see that both the outputs are same. That means if there is no tolerance, then it will be showing the same graph. So that means if we put some tolerance, then we'll be getting the Monte Carlo analysis for the same. Now this Monte Carlo analysis can be used to plot, okay. So like we can choose for 10 points or 100 points, like that also we can do that, okay. So here what we are doing is that we are just running for 1 point only. So Monte Carlo point that we are considering over here, so in this circuit we are considering only 1 point, okay. Now if you want multiple number of points, then we can use another function, okay. So we can use a particular function in order to do that. So how to do that? So we can do by having a function So let me just, so here we can use the dot fun ctio, so dot function. Okay, so we can use this particular function command. So in this function command we can just place it like whatever functions we want. So suppose we want worst case, so for worst case we can use this wc, and we can assign this function. Okay, so we can have, so here let me say we will have a nominal value and a tolerance. Okay, so we'll put this nominal and tolerance. Now we have to run this one. Okay, so we have to see like how many runs we want. So based on our run, so we can choose. Okay, so we can make the run 2 or 3 or 4, like that we can do it. So these type of functions also we can use for wc, this one. So we can use this particular wc in one of these transistors. So we can write it like this: wc, okay, and nominal value, then tolerance, and then we can put some conditions like if run is equal to 1, or you can also take like different values also, and it will be equal to nominal. And then we, let us say that if, okay, so we can either use this particular function, and if you don't want, then also it is okay. So flat 1, if flat 1 is let us say when it is greater than 0, then what will happen? So if it is greater than 0, so we will choose, okay, so nominal, so tolerance will be 1 plus minus the tolerance. So what, how can we do that? So nominal multiplied by 1 plus of tolerance, and the other value that we will have is nominal multiplied by 1 minus of tolerance. So basically what we are doing plus minus the tolerance value. Okay, so we are doing this one, so plus minus the tolerance value. Now let us see, this one is there, this bracket, okay, this one, okay. So let me have a function like this. Okay, so I'm having a function like this, function wc. Okay, so this is the name of the function. So you can name any function, you can use any other function if you want to use, and you can put some if condition, else condition, you can give that one. Now in this one, let me change this one. Okay, and here let me put wc. Okay, and I can put here the nominal value and the tolerance value. So nominal value, let us say it is 2 micro, and tolerance, so how much tolerance do we want? So suppose we want a tolerance of 5, so let us keep it like this. Okay, so we have made the tolerance as 5, and it will be, yeah, okay, so we have to make this variable. Nominal value is 2u, and tolerance is 5. Okay, the time step is okay. Okay, so here like we can do that. Okay, so here what we can do is that we can put some dot option values also, so that like we can choose the step size. So let us say the step size, let us make it 10 micro will be good, I think. Okay, so let us, dot options. Okay, so there are a lot of commands in this one, so you can just go to the help bar in this one. So you can click on this help and you can check for these options. Okay, like if you want to know the command, so you can go to the help topics, and you can find a list of all the commands over here. Okay, you can find like whatever you want to find, so you can find it. So suppose I want to know about the MOSFET model, so just click on this one, and here you can get it, the details of the MOSFET models and all. Okay, so whatever models you want to check, you can check over here. So what are the models that are available, and yeah, and even this one, what these model parameters. So the model parameters, suppose N MOSFET is there or P MOSFET is there. So if you want to know the description of those parameters, you can look at this particular help task. Okay, so you can go to this one and you can check like what is the description for this one. So this is the zero bias threshold voltage. Okay, then the next is the Kp, that is the transconductance parameter. So things like that. So you can just see what is the value CGD, CGS. So these values are already defined in that one. So from there also you can just see what are the dot options. So what can we do with this dot option value? So here you can go to this help, and you can check for this command, that is the options. Okay, so here you can see a list of different values. So dot option. So dot option you can use, how you can use. So these things are there. Okay, so these are different options what we can do. Okay, so plot win size is there, so transient temperature. So we will also see how we can vary the temperature also. So what to do if you want to change the temperature, so how we can do that. And there are a lot of things that we can do using these commands. So you can just go through this one. Okay, and you will know that okay, so these are the commands that we can do. And there are other commands, and you can also see, okay, these things are also there, like how to like change these values or how to set the graphs and all. So you can go to this help task and you can get the details. Okay, so whatever you want, all the informations are over there. So let me just make this one options max step is equal to, and go, let me, okay, point is too small. Okay, so what I'll do is that I'll choose another info. So let me open another file and let me show you. Okay, so in this particular example, so I have opened this particular example. So here, as you can see, there are like you will be able to see these particular Monte Carlo analysis. So we can actually use these functions. Okay, so basically we can use these particular functions in order to do the Monte Carlo analysis. Now here we have a function that is called as binary. Okay, and we have the worst case analysis. So here we have put the WC, and what we do is that we are doing the transient analysis and we are measuring the output voltage. Okay, and we are taking the average voltage. Okay, so this is AVG V out. So we are taking the average voltage and we are trying to plot this one. So here the number of runs we are setting it to 16. Okay, so the run is equal to 1. There I have written run is equal to 1. So here I am writing 16. Okay, so run equal to 1. So in place of 1, we can write 16. Then the nominal value. Okay, so in this case, yeah, so nominal value. Okay, so whatever nominal value. So here I am not putting any nominal values. Okay, so nominal value is there, then flat 1. So nominal 1 plus tolerance. So these values you can just cross check with this one. So if binary run index, okay, so we have to give one index and run. So this can be formed from here. Okay, so we can just use this binary function over here and we can just put some values and we can just see what is the, okay, so let me just run this one. Okay, so when we do the simulation, so here I will get the values. Okay, so this V out value, so these values that I am getting, so here if you will check how many points are there, so you can see total number of points, so up to 16 is there, right? From it is the run is starting from 0, so 0 1 2 3 4, so total number of runs is 16. Okay, and that is why it is showing 17 steps. So it is starting with 0. So 0 to 16. So I'm getting these many outputs. So this is how we do the worst case analysis, or we can say the Monte Carlo analysis. So in this one, as you can see, so when we call this one, suppose in the register I'm putting this worst case parameter over here for the register. I'm trying to find out the worst case that the register can have. So what I am doing is this: I am putting in this one, okay, and I am doing a TOLA. So TOLA and TOLB. So TOLA, so this is actually giving us the tolerance. So this is the tolerance of 1%. This is the tolerance of 5%. Okay, so these are denoting the percentage of tolerance. So here, as you can see, there is 1% tolerance for the register, and here you can see there is 5% tolerance for register. Okay, and here what are the things that we want? So nominal, tol, and index. So index value I am putting 3 for this one. Okay, so one by one. So this one is the first register that will be checked first. Okay, so this value will be varied first, then this one, then this, and then this. Okay, so the output will be checked for this, then this, then this, and this. Okay, so that is why we have put a index over here. So which one it will vary first. So that is why index is important. Tolerance we already know, and nominal because we need to have a nominal value first, and then we add the tolerance and then index, and then we run this particular system. So this is how we can do the Monte Carlo analysis. So there are two ways. One is by using this function WC. Okay, so was for finding out the worst case scenario. So we can use this particular function of WC, or we can use the inbuilt function that is called the MC or Monte Carlo. And in Monte Carlo, we have to put a nominal value and a tolerance value. So only these two values we have to put in this one. Then we can know the Monte Carlo of this one. Now, suppose we want to vary the other parameters as well. Okay, so let me just copy this one. Okay, so suppose this is our NMOS, and I want to vary all these parameters. Like I want to change the drain area, source area, drain parameter, source parameter, then number of parallel devices. So what I'll do, I'll just place this one. Okay, so I'm just putting this particular value over here. So these are the values over here, and length, let me set the length first. So length I'm fixing it. Okay, since it is a 180 nanometer, so let me just have the previous value only. So 0.5 u. Okay, so this NMOS is having this particular value. Okay, so here the value of A. Okay, so I want, like for this one I need the value of L and A. So this L and A we have to give the value of L, A, and M. Here W is also unknown. So here the unknowns are L, A, W, L, and M. So what we can do is this. So here in place of this one, we can just put L over here. And for setting up these parameters, so we can do this from here, dot param. Okay, so dot param, so this will set the values. So m is equal to 1, a is equal to 1, then L is equal to 0.5 u, and you can also set the width. So width, let me say it is equal to 1 u. So I'm setting up. Okay, so by using this particular dot param, so I'm basically setting up the values of this one. Okay, so this is a comment actually. So let me put this to spice directive. Okay, so blue line shows the, these lines are comment lines. Okay, so all these blue lines are all comment lines. These black ones are the spice directives. Now let me run this one and check. Okay, so let me first. So let me also copy this one to here, and in place of this one, let's put it over here. Okay, so here you can see the difference. Okay, so if we will zoom this one, so you can see the difference over here. Okay, so basically what we are doing, so we are doing the Monte Carlo analysis over here. So there is like you can use this Monte Carlo function and you can place these particular values. Okay, so either you can just put this into all the other parameter values, or you can place this. Okay, so this one Monte Carlo, so this length into this particular part, so this we can put it in at first. Okay, so here we can put the values, and yeah, so for this one L multiplied by, so LA is there, then this particular value is there. Then for width I am putting this particular value. For area I am putting this particular value. Okay, for source area I am putting these values. Okay, so for source drain area, for source area, so I am writing it like this. And for the drain perimeter or the source perimeter, I am using this particular formula. And the m value is nothing but the number of parallel devices. So here I am keeping the number of parallel devices as 1. And we can check. Okay, so we can just run this one and we can see what is the value over here. Okay, so these are the values and this is how we can do that. So in this one, so one. Okay, so this is how we can do the Monte Carlo analysis, and we can do the, like we can find out the parasitic capacitances. So here also we can just go to the spice error log, and if you want to see for the models, so here we are not okay. So we can just do the operating point analysis, and so here how can we do that? So go to the simulate window, edit simulation, DC operating point. So dot op, you can just run this one dot op. So once we run this one, so we get all these operating points, and we can also see the values. Okay, so here you can see the different values. Okay, so when we do the Monte Carlo analysis, so here you can see the differences in the values. Okay, so here you can see this NMOS 1, okay, PMOS 1, PMOS 2 values. So here the BSIM model files. Okay, so all those you can see over here. So what is the difference in these one? So these we can see over here. So this was about the inverter and how we can do, like how we can find out the parasitic capacitance and how we can do the Monte Carlo analysis. Now let us see how to design a differential amplifier. Okay, I suppose these things are clear. Like yesterday, so whatever queries were there, so I guess these two were many, and we have like addressed these two as well. Now today we'll be discussing the differential amplifier design. So this is a basic differential amplifier where I am taking a bias current over here. Okay, so here I can replace this with a transistor also. So that we will see when we do the characterization of an op amp. So for today, we are doing it for the differential amplifier. So let me just write down, and you can just draw this particular circuit first. So today we will be talking about differential amplifier. So differential amplifier. So today we'll be talking about differential amplifier. Now in this differential amplifier, I am using the single-ended one. Okay, so this is the single-ended. So let me just rewrite this one. So single-ended differential amplifier. So I'm using the previous files only, so 180 nanometer technology, and I have these many transistors. So two PMOS are connected like this, and two NMOS are connected in this form. Now here, this PMOS and NMOS, okay, so these basically forms a common source amplifier, and this is also a common source amplifier. So that means if we design a particular common source amplifier, the same amplifier can be copied and placed over here. Okay, so these two will be again acting as a differential amplifier only. But we'll see step by step how we can design a differential amplifier. So for designing a differential amplifier, okay, so we need to have some specifications. So let us say we are taking some specifications. So what are the important specifications in this one? So first of all is the specification that will give us the current value is the slew rate. Okay, so we need the slew rate. So slew rate, let us say slew rate is 10 megavolt. Okay, so 10 megavolt per second. Okay, or we can, yeah. So if we take slew rate like this, then what will be the value of the current? So current, so slew rate is equal to what? Slew rate is equal to current, the, you can say the bias current, and divided by the load capacitor, right? So I bias divided by the load capacitor. So from here we can find out the value of I bias. So I bias is equal to slew rate. So slew rate, if we take 10 mega, then we have to multiply it with load capacitor. So 10 pico. So let us see what is the value that we are getting. So 100, and here this is mega, this is pico. So 3, we can minus 3. So this will be 6. Okay, so minus 6, that is micro. So this becomes 100 micro. Okay, so this will become 100 micro. So 100 micro amperes. So I bias will become 100 micro amperes. And so here let us write down 100 micro. Okay, so I bias we are getting 100 microamperes. So we'll change this one to 100. Okay, so the bias current that we are choosing is 100. Now we already have this bias current from the slew rate. Okay, now okay, so let me place this one somewhere else so that we'll be able to calculate this one. So slew rate, we have got it. Okay, so the first specification. So from the first specification, we have got the I bias. Okay, so from the first specification, we have got the, from the first specification we have got the I bias. So I bias we have fixed. Now we need to know the, okay, we need to design the size of this NMOS and the PMOS. So how can we design the size of the NMOS? So the size of NMOS will depend upon the transconductance value or the gain. Okay, so for this one, we need to have the like gain bandwidth product. Okay, so from the gain bandwidth product, we will be able to know the transconductance of this one. Okay, so next specification, so we can just write down. So next is the gain bandwidth. Okay. So GBW. Okay, so the gain bandwidth product. So here we can write down the gain bandwidth product as we can have 2 pi, okay, to 25 megahertz. Okay, so let us keep it like this. So twice of pi 25 megahertz. Okay, so the gain bandwidth we are taking, so 25 megahertz. So here GBW, okay, the gain bandwidth product is equal to GM, okay, so GM divided by twice pi into C load, okay. So this will place it here. Yes. So gain bandwidth product. So from here we will find out the value of GM. So what is the value of load capacitance? So already we have this 10 pico. So we'll get the value of GM over here. So twice pi, twice pi. So we can cancel this out. And sorry, this twice pi will be multiplied to that one. So gain bandwidth product multiplied by. So otherwise what we can do is this. We can take the gain bandwidth product as 25 megahertz, and the gain bandwidth product is equal to GM upon twice pi into CL. Then the transconductance GM will be equal to twice pi C load multiplied by the 25 megahertz. So 2 into 3.14 multiplied by the load capacitance. So this is 10 pico farad, and this will multiply with 25 megahertz. Okay, so this will give us the transconductance. So let us just quickly calculate what will be the transconductance value of this one. So 2 multiplied by 3.14 multiplied by 10 pico multiplied by 25 megahertz. So since it is a pico, this is mega, so these two will make it micro, right? So these two will make it micro. So we can just write down this value. So 1570 micro. Okay. So we are getting this particular value. Now we can also write down this as GM is equal to 1.57 millisiemens. So we have got the transconductance value. We have got the current value, we have got the transconductance value. Now how we will find out the transistor size over here? Okay, so we have to put it into a formula. So first we shall know what is the current that is flowing through here. So the current that is flowing through here is 50, and the current flowing through this branch is also 50, because the total current is 100. So we need 50 ampere to flow from this part and 50 microamperes to flow from this part. So I'll quickly write this one. So 50 microamperes from each side. Okay, so 50 microampere current is flowing through this, and 50 microampere current is flowing through the other side as well. Okay, so 50 from here and 50 from here. Okay, so now we know the current. Okay, we know the transconductance value. Then we will be able to find out the size of this one. So for finding out the size of the M1 transistor, so let us try to find out the size of the MOS transistor. So for finding out the size, what we can do? So third, you can write down size of M1 and M2. Okay. So for finding out the size of N1 and M2, so we will put the formula. So the size, let us represent it with the dimension. Okay, so W by L of 1 comma 2. Okay, so W by L ratio will be equal to what? So GM square. Okay, so GM square divided by it will be, so GM square upon ID. Okay, so the drain current of this one. So this will be equal to ID of 1 or 2. Okay, ID of 1 and the value. So that we will say it is Kp. So what is Kp? So this is equal to mu1 Cox. Okay, so Kp, let me write it down. So Kp is equal to mu C ox, okay, into C ox. So this is the value of Kp, and ID is nothing but the drain current. So here, as you can see, so we can put this formula. So Kp is equal to mu C ox. So if we place it in this particular formula, so this will be equal to this. Okay, so ID. So this is there. So gm square. So this will get cancelled out, and here, so here one more term will be added. So this is twice of that. Okay, so ID is equal to half. Okay, so sorry, this is equal to 2 multiplied by ID multiplied by Kp. Okay, so I might have written it wrongly. Let me just correct this one. Okay, so twice of ID and this value. So yeah, and this is equal to. Okay, so just let me recheck this one equations. I think this is gm square upon. Okay, so this is actually gm square upon twice of, yeah, gm square it will be. Okay, so we can have this one. So we can put in this whole formula. So gm square divided by this. So gm value we already have from this equation. We already have the gm value. Now we divide it twice into ID1 into Kp. So what is the value of ID1? So ID1 is half of this. So this is equal to 50 microamperes. Okay, so we'll multiply this one, and what will the value of Kp, that is a mu p Cox or mu n Cox. So these values actually we can find it out from the model of the particular transistor. So here, as you can see, so let us go to the help topic. So let me show you from where you can get this particular value. So when we check the model file of N MOSFET and P MOSFET, here you will find a term that is written here. Okay, so it is written as Kp, the transconductance parameter. So these values it will be given to you. Okay, so these values will be given to you, and if Kp value is not given, then you might get a beta effective value. Okay, so there, like in the model file, you will either get this Kp value or you will get a beta effective value. So beta effective and Kp, so what is the difference? So Kp and beta effective. So in beta effective, we have the transistor size as well. Okay, so Kp is equal to mu C ox, and beta effective is equal to Kp. Okay, so Kp effective multiplied by W by L. Okay, so W effective divided by L effective. Okay, so Kp is equal to this and beta effective is equal to this. So from here we can easily find out the values of mu Cox. Okay, either we can use this or this. So any one of these we can use it to find out the mu Cox value. Now this value, so for the timing, let us, for this one, okay, since it is a 180 nanometer technology, so for this one let us consider this as 100 micro. Okay, so if we are considering this as 300 micro, then what will the value of WL? So here we will see GM square. So GM square means 1.57. Let us say this one. So 1.57 square. Okay, and divided by twice into ID. So twice into ID means 100. So divided by 100, and it is divided by Kp value. So Kp value we have taken over here is 300. Okay. So we'll get this one, and so this one, let us write down the value that we are getting. So 0.00082, and here we need to check this one also. So gm square, so milli into milli, that will become 10 to the minus 3 into 10 to the minus 3, that is 10 to the minus 6, divided by id is in microampere, so this is 10 to the minus 6, and kp is equal to 300 micro, so this is also in micro. So this becomes 10 to the 3 multiplied 10 to the 3, so 10 to the 6. So if we do that one, so this will become 10 to the 6. So 1, 2, 3, 4, 5, 6. Yeah. So this will come to 82.16. Okay. So the ratio of this is this. Okay. So 82.16. So this is the ratio of W by L. Okay. So we have this particular ratio, W by L ratio, we have got this. Now we need to find out the value for M3 and M2 transistor. Okay. So we have calculated for this M1 transistor, W by L ratio for this NMOS transistor. Now we'll do this for the PMOS transistors. So for PMOS transistors, what do we know? So this current flowing through here. So okay, so here we can calculate this one by putting up a formula. So let us calculate this as well. So actually the calculation, okay, the designing part may differ from, like, for me it is different, for you it can be different. So the basic idea is to find out the W by L ratio for all these transistors. So now what I can do is that, so the current flowing through this one, that means I3, okay, is equal to half of, okay, so 0.5 multiplied by I bias. So I will use this particular formula, that is I3 is equal to 0.5 of I bias. Then what will be I3? So what is the formula for I3? So I3 is nothing but mu p Cox. Okay, so mu p Cox. So here what we can do is this, like here in place of Kp, I can write down Kn. Okay, so I can write down Kn. Now in this case, I3 value, so I3 will be what? I3 is equal to mu p Cox, right? Half of, so you can write down 0.5. So half of mu p Cox, so I can write down Kp multiplied by W by L of P. So W by L of P, then this will be multiplied with VSG minus of VTHP and square. Okay, this is the condition for the saturation region. Okay, so when we are considering an amplifier, so here we have a differential amplifier, so we must make sure that all the transistors are in saturation region. Okay, so these are working in the saturation region. So if you consider that, so our saturation region formula is this. So this will be equal to I bias. So 0.5 multiplied by I bias. So we have got this one. So from here we can find out the value of WL of 3. So in this case, we will consider the value of Kp. Okay. So here the value of Kp. So basically Kp is equal to mu P Cox value, and this we will consider as 80 micro. Okay. So earlier we have considered this one Kn as 300. So here Kp value we will consider it 80 microvolts. Okay. So we have considered this one. So we have got the Kp value over here. So let me just focus in this one. So here we have the Kp value over here. Okay, so we have got the Kp value over here. Now what do we need to do? So now we need to find out the W by L of 3. So what will be the W by L of 3 here? So just calculate this one. So what is VSG? What is the value of VSG? Then what is the value of VTHP? So these values we need to calculate first in order to calculate the value. So we will calculate first the value of VTH of P. So VTH of P is the threshold point of the PMOS. So where can we get this particular detail of this one? So we have to look for the this one. We have to look into the model file. So there we will find a term that is VT0, and you have to do this. So plus minus. Okay. So plus minus of 10%. Okay, so plus minus 10% of VT0. So what value we'll get? So here like VTHP is equal to VT0 plus minus of 10%. So you, if we want VTHP maximum, okay, so here you can either have VTHP maximum or you can have VTHP minimum. Okay, so VTHP maximum. So VTHP maximum will be VT0 plus of 10%, and VTHP minimum is equal to VT0 minus of 10%. Okay. So VTHP can be written like this. So we will consider the minimum portion. So here it is somewhere near about 3.99. So here let me consider this as 0.4. Okay. So these are near about 0.4. So I am considering this as 0.4 volts. So VTHP I am considering 0.4 volts. So similarly I can have VTHN. Okay. So the threshold of NMOS also. So in the same way we can have the threshold of NMOS as well. So what will the threshold of NMOS? So VTH of N. So the maximum value of that is equal to VT0 plus of 10%. And this also, let me consider this as 0.4 volts only. Okay, let us say it is equal to 0.4. Okay, so this value I am getting it from the model file. So model file, suppose VT0 value is 0.35 or something. So I am just considering the value near to that one. Okay, so I am considering the nearest value, but you can do this also. You can take the maximum value as 10% variation in the VT0 value, and the minimum value if you want to calculate, then you can do this one. You can subtract this one. So minus of 10%. So that you can do that. So these are the things in this one, and we have got this. So VTHP and VTHN. So let us see how we are going to make in this circuit. So VSG. So what is VSG? So VSG is equal to VS minus of VG. Okay. So since this is for the PMOS, okay. So here the VSG value is equal to, so we can write down VDD minus of VG of the PMOS. Okay. So VG of the PMOS. So here you can see the gate of the PMOS of M3 is connected to the drain of the PMOS, and this is also the drain of the NMOS. Okay, so let me put a comment in this one. So D Okay, so the drain of these two are the same, and the gate of this PMOS is equal to the drain of this PMOS. Okay, so the drain voltage and gate voltage both are connected together. Okay, so the gate and drain, these are connected together, and the drain of this is also equal. So here we have this VDD minus of VGP, and we have this VG of P is equal to VB of N, and this is equal to, so since we are considering the saturation region, so VD value should be greater than, or we can say greater than equal to the VGS minus of VTH value. So VG of N minus of VTH of N. Okay, so VG of N minus of VTH of N. So we have this one, so VGN minus of VTH of N. Now we will put over here the value of this one. So let us put there. Okay, so this is there. So VSG is equal to VS minus of VG equal to VDD minus of VGP, and VGP is equal to VD of N, and this NMOS drain is equal to the gate, okay, gate of the NMOS minus the threshold voltage. Okay, so this is the condition for the saturation region. So with this one, I'm putting this particular value. Okay, so VGP is equal to VD of P, and VD of P is equal to VD of N. So from here we have. So once we have got this, okay, so what is the value of VTHN? So that we already know what is the value of VTH of N, and what is the value of VG over here. So this value of VG will depend upon the common mode range. Okay, so input common mode range. So the maximum input that we can consider. So let us say for this 1.8 volts, I am considering the value of VG of N equal to 1.6. Okay, so this is the maximum value that we can, like, input common mode value that I am taking is 1.6. Okay, and this threshold value is 0.4. So let me put the values then. So if, so let me put this value over here. So VG value is this, VTH value already we have got. So VG of P value, we can get it. And this is equal to, so VGP is equal to VG minus of VG, so 1.6 minus of 0.4, and this is equal to 1.2 volts. And here we need to subtract these two, so this is 1.8 minus of 1.2, and this gives us 0.6. So we have got the value of VSG over here. We know the value of VTHP. So we'll put it in this particular equation over here. So when we put the values in this particular equation, so this 0.5 and 0.5 will get cancelled out. Okay, 0.5 from the left hand side and 0.5 from the right hand side. So these will get cancelled out. Now we are remaining terms are KP, WL of 3, VSG, and VTH of P. So here we'll put the value of Kp over here. So Kp I'm considering 80 micro. So I'll put 80 micro multiplied by W upon L of 3 multiplied by, now this is VSG minus VTHP whole square. So what is the value of VSG over here? So VSG value I am getting 0.6. So 0.6 minus of 0.4 is equal to 0.2, and 0.2 square will give us what? We will get 0.04. 0.04. So this will be the VSG minus of VTHP square. Okay, so VSG is equal to 0.6, VTHP is equal to 0.4, the total term is 0.2, and the square of 0.2 is 0.4. So that is why we are getting this value, and this is equal to the I bias, because we have already cancelled out the 0.5 in both the sides. So we have to multiply with I bias, and the bias current that we are considering is 100 micro. Okay, so we have considered this as 100 micro. Now, what will the value of WL of 3? So micro will get cancelled out. Okay, this is micro, so these two will get cancelled out. Now we will just do the multiplication and division. So what will be the value of W by L of 3? So we'll write this one. So W upon L of 3, this will be equal to, so 100 divided by 80. Okay, 100 divided by 80. Okay, so this gives us 1.25 multiplied by, okay, so sorry, divided by 0.04. So this will give us the value 31.25. 31.25. So this value we are getting, so 31.25. So this is the value of this. So now let us put the values over there. So W by L ratio we are getting 31.25, and the other ratio that we are getting is 82.16. So if we consider the length of this PMOS and NMOS equal to 1, okay, so let me just down. Okay, so the width and length. So W by L is equal to 82.16. Okay, so if I choose L equal to 1 micro, then what will be my W? So W, I have to take 82.16 micro. Okay, so this is for the PMOS, and I will again consider this for the NMOS as well. So let me just shift this one a bit further. So now let me choose this. So for the so let me again comment this one, and in so WL of 3 is equal to 31.25. So if I choose this as 1 micro, then this will be 31.25. Okay, so this one is this. And okay. So here we are getting, so 31.25 is for this M3 and M2, and this is for the M1 and 4. So we can also just rewrite this one as M2. Okay, so I'm changing this. So M1, M2, M3, M4. Okay, so I'm changing the name of the instances. So it is like this. So now we have sized the transistor. So let us size this transistor accordingly. So length we are taking 1 micro, and the size of the NMOS I'm getting over here. So 82.16 micro. So this I can directly copy it, and I can place the value over here. So directly I can get here. And for the PMOS, the length is 1 micro, and the width is 31.25 micros. Okay. So let me just make the transistor size accordingly. Now let me save this one. Okay. So now we have saved this one. Okay. So we have got these particular values. Now we have to give some input to this particular differential amplifier. So we have sized the transistors according to our specification. So this is our specification. So according to our specifications, we have sized the transistor. So after sizing the transistors, now we'll check how much gain we are getting, what is the slew rate that we are getting. Okay, so then we can also calculate the power dissipation or other things in this particular differential amplifier. Okay, so we can do the AC analysis for this one. So let us try and do this. So first, let us do the transient analysis for this one. So let us just do the transient analysis. Okay, so for transient analysis, okay, so I will click on the output voltage. Okay, so for transient analysis, what I am choosing, so here I have the V in, okay, the negative portion. So I am taking this amplitude as minus of 10 millivolts. Okay, frequency I am taking 100 kilohertz. In the V I and P, I am keeping the AC amplitude as 1. Okay, this is required when we do the AC analysis. And here the inputs. So for this one, I am giving 10 milli. In the V1, we have given minus 10, and for this one, V in P, I am giving 10 milli. So let me show, then it will be clear. So when I click on this output voltage, so here you can see this, there is a output voltage over here, shown over here. Now let me put another plane over here. Okay, so this is the V out plane. So here what I'll do, in this particular plane, I will click on add traces. Now here I'll select the inputs. Okay, so VIN N and VIN P. So this I have selected. Okay, so here I'm getting the transient analysis for this one. Okay, so this is how we are getting the transient analysis for our differential amplifier. So here, as you can see, for this particular difference, okay, so the V in and V and P. So these are all what? So you can just click on this V in and V and P. So you can see the maximum. Okay, so from this 0.9 millivolt. Okay, so this 0.9 millivolt, it is the common mode voltage that I am taking. So this 0.9 volt. Okay, so this is the common mode voltage, and this, so there is a line 0.9 and above that and below that. So I'm drawing a sinusoid in that mode. So this is my input, okay, so IN and INP, and this is my output signal that I'm getting, okay. So here, as you can see, it is going up to 1.7, and here it is going up to 0.4. Okay, so I'm getting this particular transient curve. Now, if I want to do any other, so here what I can do, I can find out the delay or anything like I want to do with the transient analysis. Now we will look at the AC analysis for this one. Okay, so we'll do the AC analysis for this. So for AC analysis, what do we do? So we can either have a decade, right? So here, as you can see, in the AC analysis, we have to mention the sweep that we are doing. So either we can click on octave or decade. Okay, so you can choose any one of these. You have to select the number of points. So here I am selecting 100. The starting frequency I am choosing is 10 hertz, and the stop frequency I am choosing over here is 100 megahertz. Okay, so in the megahertz you have to write down MEG. Okay, so if you will write down capital M, so it will not count it as mega, it will count as milli. So that's why we need to make sure that we have written MEG. Now we have made this one as this. Now we'll run this. Okay, so yesterday someone was asking that can we plot these two at the same time. Okay, so we cannot do the two at the same time. Okay, so here you can see, like, even if I selecting this one, so I am actually doing the transient analysis only. Okay, So for AC analysis, let me click on this one. So once I click on this, okay, so once I click on the output, so here we can see the magnitude and phase. Okay, here we can see the magnitude and phase of this one. Okay, so we can locate the pole. Okay, so which will be somewhere here near to this 3 dB minus 3 dB point. Okay, and we can also find out the gain. Okay, either we can use the dot measure command to find out the gain, or you can directly click on this V out. Okay, so once you click on this V out, here you can see, okay, so it is written 39.89 dB. So this is the gain, okay, or we can say the magnitude that we are getting. So this is the gain of this particular differential amplifier, and you can see, okay, so here when we make this magnitude as 0 dB, okay, so this when it becomes 0 dB, then we can see what is the phase. Okay, so this will give us the phase margin. So now when we move this one towards 0 dB, okay, so you can see the phase over here. So this is near about this. Okay, so we can just zoom into this particular portion, and we can just choose this particular value over here. So if it is near to 0, then it's more better. Okay, so here as you can see, like we can actually zoom this one. Okay, so we can actually go near and near, and we can just select a particular value for this one. So we can just click on this. So here I have labeled this one. Okay, so this is 3 point like micro dBs. So it is actually 0 only. Okay, so it is in 0 only. So here you can see it is 15.44 megahertz. Okay, so here we are getting 15.44 megahertz value. Okay, so this is how we do this one. Okay, so we find out the gain, bandwidth. Okay, so these things we can calculate from here. So at 0 dB, what is the phase margin? You can see what is the bandwidth. You can see over here. Then from here, so you can measure the bandwidth and all from this point. Okay, so from V out you can measure. Okay, and here like you can see when this phase and gain are crossing, so you can check at that particular point that what is the like frequency. Okay, so here gain and frequency, so you can see what is the like how many kilohertz or megahertz we are getting over here. So these are the things in this one. Okay, so these things, so basically we do what we do is that we basically find out the gain bandwidth product, and here you can do this kind of multiplication and you can do this. And one more thing that you can do is that use the dot measure file. Okay, so in the dot measure file, so if you already have this dot measure file, so you can just click on this waveform window, go to execute dot measure script, and you can just click on your measurement and you can see the values. Okay, you can see that at 0 dB it is 39 dBs. Okay, so sorry, at 0 degree phase, so it is 39 it is showing. Okay, and like what is the value that we are getting? So we are getting this much phase. Okay, and here you can see the gain. So the gain is this. Then the value in 3 dB it is this. Okay, and like gain divided by square root, so minus 3 dB point is this one. Okay, so 37.06, so this is the minus 3 dB point, and we can find out the bandwidth. Okay, so which is this 15.37, right? So 15.3784. So here what we are getting, the bandwidth that we are getting is 15.44 megahertz. Okay, so we are getting this 15.44 megahertz over here. So this is how we do the simulations in this one. Okay, and for finding out the slew rate, what we do is that, so for finding out the gain, we do the like if you want to find out the gain and phase, so we do the AC analysis. Now if I want to find out the slew rate for this one, then what I will do, I will do the transient analysis. And if I need the operating point for this particular amplifier, or if I want to have, or let us say if I want to have the DC analysis for this one, that also I can do. Okay, so what I can do is that I can just click on this button. So in the edit simulation button, so here I can sweep this one. Okay, so in the DC sweep, what I will sweep here, so here I'll put the source name as VCM. Okay, so I will carry the common mode value and remaining other values, so that actually I have to make it 0. So type of sweep, so let us make it linear. Starting value, let us say it is starting with 0 and ending with 1.8, increment of 0.1. So we can see the input output relations in this one. Okay, so input we are varying, and this is the output that we know. So here you need to like replace this like VIN and VNP with a DC value. So here we have to make sure that these are 0 0. Okay, so or let us save this one as differential amplifier underscore AC. Okay, so this will for the AC analysis of this one. So let me save this one, differential amplifier AC, and then the next I will do for the DC. So for DC I will remove these two. Okay, or I will make these values as 0 0. So I'll choose the DC value as 0 for this one, and for this one also I will choose here the DC value as 0. So I have chosen the DC value as 0 0, and here what I am doing, so I am doing the DC simulation, so I am changing this VCM value. Okay, so this VCM value, that means I am changing the value for VIN and VNP. So or else what I can do is that I will only change one of these. Okay, so I will change the value of VNP and I will keep the VIN same. So that also I can do. So let me choose this instead of VN. So let me, this is V3, and I'll choose the starting value as minus of 0.9 and stop value I'll choose 0.9. Okay, so if I choose like this, so this is minus and this is plus, so this means total is 1.8. Okay, so like this one will start at 0 because minus 0.9, so it will start at 0. Then I will keep on reducing it, so plus of this will become 0.8, so like this, so 0.1, 0.2, so it will increment like that. So now if I run this one, then I'll choose on the VNP. Okay, so here you can see the input at P. And then if you click this one, so this is the input at the N side, and then I click on the V output. Okay, so when I click on the V output, so you will see a graph in this form. Okay, so when you get a graph in this form, so you will know that what is the offset. So what will be the offset in this case? So you see this point and this point. So what is the difference between these 2 points? So the difference between the point over here, okay, so the intersection point of this one and the intersection of this particular V out with V in will give us the value. Okay, so how we can do that? So we can either like use the dot measure, or we can also have another like value, so dot step, and we can do this parametric analysis, or sorry, not parametric. So we can use that dot MEAS. Okay, and we can actually measure that one. Okay, so here what we can do, we can choose the analysis that we are doing. So we are doing the DC analysis, and here we can just name this one as offset, and from here we can choose. Okay, so what do we want to find? Okay, so the integration, this, and we have to find out the derivative, or we just need to find. Okay, so we have to find, so what will the measured quantity, so which quantity we are going to find? So v of v out we are going to find, right? So v of v out we are going to find when v in is equal to v out. Okay, so we'll write down when v of v I and n is equal to v of v out. Okay, so when v in is equal to v of v out. Okay, so cos, so we can just test this one. So here you can see v out is equal to d of v. Okay, so offset is equal to d out equals this, and at this point, okay, 0.031. Okay, so 0.031 means 31 millivolts. Okay, so this is 31 millivolts. So at 31 millivolt it is crossing. So let us just cross check with this one also. So we can just zoom in over here, and you can see it is crossing at 31.7 millivolts, right? So 31.7 millivolts. So it is crossing at 31.7 millivolts. So here you can just see. So you can just click on test, and it will show you at what point it is clearing. Okay, so the offset, we'll try to find out the offset. So first we'll just rename this one. Okay, so let us not call it offset. So instead of offset, so let us call it as the V out VIN intersection, right? So INTER1. Okay, so this is the intersection 1. Okay, so I have saved in the name of intersection 1. So I have got this particular intersection value. Now I need to find out this intersection value as well. Okay, so what will the value of V in, or let us say what will the value of V I and P at this particular point? So for that one, what I can do, I can just copy the same formula, okay, and I can again paste it. So I can just copy this one, is the same thing. Now here I will write down this one as INTR2, and here find the value of VINP. Okay, so instead of V out, now I will write down VINP when V in is equal to VINP. Okay, so now this will give me the value. Okay, so this will give me this point. Okay, so this intersection point, and the other will give me the other intersected point. So what I will do, I will find out the difference between these two. So INTR1 minus of INTR2. So again, so either I can use the param, or I can directly write down measure offset is equal to INTER1 minus of INTER2. Okay, so the difference between these two. So the difference between these two will give me the offset value. So I click on OK, and let me rerun this one. So once I rerun this one, let us go to the error log. Okay, sorry, not the error log. So we have to go to the spice net. Okay, so here you can see. Okay, so this, okay, so there is some mistake in this one. So it is showing minus of 1.3877. Okay. Okay, so let me just reframe this one. Okay, so it is not showing when v in is equal to this. Okay, fine. So it is 0.9 where it is intersecting. But the value that it is showing is somewhat less. Okay, so minus of 1.38 e to the power minus of 0.016, but it should not. So this we can write down VINP. Okay, VINP when it reaches 0.9. So this will actually give us the value. So 2.38. Okay, so what we can do is that, okay, so let us for the time being just keep it the same. Okay, so you can just click on this one and let us check what is the value that we are getting. So spice, so we can actually form this one. Okay, so the intersection, I don't know why it is not showing like this, but it will actually show the point where it is intersecting. Okay, so when we write this particular command, so it should show. So VINP is equal to 0.9. So VINP is equal to 0.9 at this particular value. Okay, so this particular value is very very small, so maybe because of that it is showing. So okay, so this is near about zero actually. So why it is showing like this? Because it is near about zero. Okay, so this point is zero, so the difference between these two will be what? Okay, so that means our equation is correct. So this point, the point of intersection between the VIN and VNP, so it is zero. So here the mark is zero, and this particular V out P, so it is crossing at this particular point. Okay, so if we take the difference between these two, then we can get the output. Okay, so we have to take the difference between these two. So what will the difference between these two? So this will be actually equal to this only, 31.7 millivolts. Okay, so this is the offset. Okay, so this will be the offset. So directly, like instead of writing all this, like when Vn is crossing this one, okay, so instead of writing this one, so we can directly actually omit this one, and instead of inter one, we can directly write down this as offset. Okay, so for measuring the offset, so we just need to know when the V out is crossing this line. So once we know when the V out is crossing this particular line, so we know the offset. So what will the offset? So the offset point is from here to here. So the offset point is 31.7 millivolts. So offset is 31.7. Now it is going towards that. So if we do this, like if we add minus 31.7 millivolts, okay, and then if you try to run, okay, so then you can see what is the value that we are getting. So you can check in the spice error list. Okay, okay, so I am only varying this one V3 value. So okay, so here there is no change in that one. So let us place in the DC value here. So 31.7 milli. If I place it on this side, and let me make this one as 0 and run this. Okay, so here you can see the offset changes. Okay, when we are putting some voltage, okay, so we have to put a common voltage to this one. So this will actually change. So 31 millivolt. Okay, so 31.7 like that we have to put. So if we add that particular amount of voltage, so then we see that it will become or it will come closer to this. Okay, so here now it is showing 0.285941. So actually why it is doing like this, because like here what we need to do is that when we do this particular DC simulation, so here we need to add an offset. Okay, so here we need to add an offset to the input. So when we add an offset to the input, then the value, okay, so we have like the main objective is that for from the DC analysis we have to remove the particular offset. Okay, so here also like we have to remove the particular offset by making this. Okay, so by adding a voltage to either this or this. Okay, so if I add some voltage towards this, so the value will change. So if I add, so here like we need to, suppose in this one we need to shift this to this particular point, right? So actually I calculated at this particular point, but I have to calculate at this actually, like what is the offset voltage at this particular point. So this value actually I have to calculate that what is the value at this point, but I have calculated at this point, so this is wrong. So at this particular 0, what is the value of V out? So that I need to calculate actually. So let me check that one. So when V in IN is equal to, Okay, so it is near about 1.49. So I will put 1.49 over here, and I'll resume with this one. Okay, so I'm getting this VN. Okay, so I'm changing this one. So here, as you can see, so as I increase the, like if I add some voltage in the N side, okay, so that is actually cancelling this one, and it is trying to move this particular V out towards the intersection of V in and V and P. So once it is collided with this one, so we have removed the particular offset. So we have to keep on checking this, that what is the value that we are getting. So whenever we are putting some value to this one, so actually increasing. Okay, so it is near about this one. So basic idea is to remove this particular offset. So whatever offset we are getting, so we need to remove that particular offset actually. And for removing that offset, we need to add a voltage either to the N side or the P side. Okay, the idea is to add a voltage towards N side or P side to remove the offset in this particular circuit, that is the differential amplifier. Okay, so these are some of the analysis. So we can do the AC analysis, we can do the DC analysis. So DC analysis we mainly do for finding out the offset. So let me just write down here. So basically we do the DC analysis for finding out the offset. Okay, so DC analysis in order to find out the offset and correct the offset. We do the transient analysis. Okay, to find out the slew rate. If you want to know the slew rate, so we will do the transient analysis. And if you want to know the magnitude or the phase, so for that one we can use the, so I can write down gain, bandwidth. So for gain and bandwidth, we do the AC simulation. Okay, so these are the simulations that we do. So then if you want to plot the phase, okay, so you can use the ph command. Okay, for phase, if you want to know the phase, suppose you want the phase of a voltage, so you can write down ph, okay, and v of v out. Okay, so v of v out, so this will give you the phase. And if you want the magnitude, then you have to write down mag, and v of v out. Okay, so ph v of v out will give you the phase, and for magnitude you can write down magnitude of v out. So these are the two commands. Like if you want to plot only the phase, then you can use this ph v of v out. If you want magnitude, you can do this. And if you want to find out the derivative, suppose you want to find the derivative, so you can use the d. Okay, capital D you can use, or small d will also give you the derivative, and you can write down v of v out. So this will give you the derivative. So these are few commands in this one, and we can do these analysis in a differential amplifier. So we can do the DC analysis, we can do the AC analysis, we can do the slew rate, we can find out the slew rate from the transient analysis. So we have seen in the DC and the AC. Now we'll see the transient analysis. So for transient analysis, what we'll do, we will make this one as 0. Okay, and here since VCM we are already keeping it as 0.9, so we will choose a pulse from minus of 0.9 to 0.9. Okay, why we are choosing this? Because of the VCM value that we already have. So delay, let us say it is 10 pico, or let us make it 100 pico. This rise time 100 pico, 100 pico, and on time, let us say it is on for 100 nano, and the time period is 200, or let us make it 220 nano, and let us say there are 10 number of cycles, and let us click. So now let us run this one and find out the transient analysis. So when we do the transient analysis, okay, so we do it for this one. So this, okay, so we are doing this for the 2.2 microseconds. So here you can see the transient analysis for this one. So here V in is there, V and P is there, and we are finding out the transient response for this one. Now we are not getting a proper response, so that is why we are not getting the values properly. So we can actually design it, and let me choose a lower value for this one. And let me take this as 10 micros. Okay. So I'm considering this for 10 microseconds. So we can see, or we can also say this one as. So as you can see over here, so V in and V and P. So you can see the V output over here. So output is a transient response over here, what we are getting. So how to calculate the slew rate? So there is a positive and negative slew rate. So this, when the output is changing from high level to the lower level, so this is called as the negative slew rate. And when an output is increasing, okay, it is going from 0 to the higher amplitude, or we can say the lower potential to a higher potential, then this will give us the positive slew rate. Now what we will do, we'll add up these two. Okay, we'll take the average of these two, and that will give us the actual slew rate value. Okay, so we need to make sure what is the slew rate that we are considering. Okay, so here in this case I have taken as 10 mega, so we can take actually lesser than that. So 10 mega is actually a lot more, so we need to keep it a bit smaller. Okay, so there are things like this. So we just need to know how to calculate the different values and how to design this one. Okay, so if there is any query regarding this one, like how to do the differential, so how to do the simulations for the differential amplifier using LT Spice, you can let me know. Okay, so let me check the message box. So here Kavita has asked, for any tech node, how to consider maximum and minimum value of length. Okay, for any technological node, see, the minimum length will be given over there. So it will be given in the model file itself. So let me copy a particular model, then it will be clear to you. So let me take up a model file where it is mentioned. So actually it is mentioned over there, like what should be the minimum length. let me just. Okay, so the model file, so it looks somewhat like this. Okay, so here you can see the model file. So here you will see a lot of parameters are there. Now in this one, here I don't think it is mentioned over here, but here only this term. So VTH 0 is mentioned over here. Okay, the VTH 0 value is mentioned. VTH 0 value is mentioned over here, and so you can just check in the model files. Okay, sometimes it is given over there that what should be the minimum length and minimum width. So in the fabrication model files, so there you will see this actually. So let me just look at it. Okay, so the oxide thickness is given over here. So W, so LWN is given. So actually you will find it in the model file itself. So there will be a minimum length or minimum width. So that will be actually defined over here. That what is the maximum width that you can take. So it will be also mentioned over there. Okay, like you will actually get what will the maximum width and what will the maximum length. So that is also actually given in the particular model file. So let me see if I have such kind of model files with me right now. So let me just check. If I have this model file, then I can show you that yes, it is given actually. So let me just cross check it. Okay, so actually, okay. In some of the model files, actually, it is mentioned that what will be the, because I have to go through it through the model files in order to know that. Okay, because like I have to check which one or which are the parameters that are given to you. But in most of the model file, it is given. And what you can do is that like because in 45 nanometer, okay, so if suppose I am using a 45 nanometer technology, so the like actual weight, or you can say that the actual length, okay, so it varies. So what do we consider is the effective length or effective width actually. So whenever we do the simulations, we consider the effective length and effective weight. So for that, what you can do is that instead of choosing the lowest length, okay, so instead of choosing, say for example, if you are choosing for 45 nanometer technology and you are choosing 45 nanometer length, so that may not give you the actual value, okay, like it will create some problem. Why it will create some problem? So like because it is not consistent, that value which we are taking is not consistent. Like if you use the fabricated model files, then you'll get the actual values, but if you don't use the fabricated file, then like there will be some difference in that one. So let me just check if there is anything given there. Because whatever files are available in PTM, so these are actually generic files. So these are not the actual fabrication files. These are generic files that we get in PTM. You can edit those files and you can use those, but you cannot use those files for fabricating any circuit. So these are basically generic files. And for TSMC, like for 180, like if you will check the website of MOSIS, okay, so you can go to the MOSIS website, and then you can check, okay, and you'll get these values like the mu and Cox values, and you can get the VTH value. So these values are actually given in that one. So I am not. So there will be like you will get a file which in which it will be written like MOSIS wafer acceptance test. Okay, so there they mention the VTH and all those things. And effective length or width, what you can do is that for effective length and width, you can choose with greater than that. So suppose say you are using 45 nanometer, so you can choose 50 or 60 nanometer. So don't choose 45 nanometer itself. You choose 50 nanometer or 60 nanometer. Don't choose 45 nanometer. Okay, because that 45 nanometer will not work when you will fabricate. So it will give you some difference in that one. Okay, so it will be different in that one. Okay, so here is one, so which I can actually share, I think. So let me just paste it. So let me just paste it over here, and I'll show you that what are the details which is available. Okay, so okay, so here like you can get a file from the MOSIS. You can get a file. Okay, so the file will be somewhat like this. So it will be like MOSIS wafer acceptance test. So it can be for an IBM technology or it can be for a TSMC. Okay, so you can get it from the MOSIS website. This particular file will be available to you, and even the model file will be also available to you. Now you can look. Okay, so if you look into this particular information, so you will get the VTH value. Okay, so there it will be mentioned that what is the minimum VTH value. So here it is, say here it is given 0.24, 0.18. So the VTH value is 0.24 for NMOS, 0.18 for PMOS. Okay, so here N channel, P channel. The first one is N channel, the second one is the P channel. So the minimum is 0.24, the maximum is minimum is 0.18 for P channel. Now the VTH value is 0.46 for N channel and 0.43 for the P channel. So these things, these details are given in the MOSIS website. So you can collect these particular details and then you can use it. So here you can see the wide, okay, so 20, and here it is 0.18. Okay, so let me just show you. So what can be the width and what can be the length? Okay, so this much width is there. Okay, so this much wide it can be. So how much wide it can be? So 0.18 and 20. So the maximum it can have a dimension is 0.18 and 20. So that means the length can be 0.18 and the width can be 20. Okay, so this is the dimension. So width and length. So actually this is wide and large. So how much large it can be? So it can be 20 into 20. Okay, so the whole wafer. Okay, so if you are drawing it in a wafer, so this can be 20 into 20. Okay, so this like a square box you can imagine. So 20 into 20. And the maximum and minimum values that we can have is 20 for the width and 0.18 for the length. Okay, so these are the values that you can collect from here. Okay, so if it is larger, so here see when it is shorter, when it is minimum, then the VTH value is this. When it is short, then the value is this. When it is wide, the value is this. And when it is large, the value are these. Okay, so these are the, so this is nothing but the W by L ratio. Okay, so minimum W by L ratio is this, short W by L ratio is this, wide W by L ratio is this, and the large W by L ratio is this. So you can start with 0.18 to 20. So this is for this particular technology. Okay, so this is 180 nanometer technology, which is available with the MOSFET. So it is, the vendor is IBM. Okay, so if you are using a IBM 180 nanometer technology file, just you, what you need to do is that you need to collect the results. Okay, so here you can see MOSFET wafer acceptance test. So you need to collect this particular information, which is actually available with the MOSFET, and you can see what is the minimum width or length that you can have. So here you can see the minimum width that you can have is 0.24, and the minimum length that you can have is 0.18. The maximum and minimum length and width can be 2020. Okay, so these are the files you need to collect actually. And there also, like, you can also find this one. Okay, so if you want to find out the mobility, okay, so mu and cox value, okay, so this value, the mu and cox value also you can get it. So this is also mentioned. Okay, so what will be for the N channel, what will be for the P channel, so it is also given. Okay, so Kn, so this is mu naught cox upon 2. Okay, so the K dash value, so for N channel it is 153.3, for P channel it is minus of 32.1. So these values, okay, so this 153, there's a minus of 32. So these values you can find it. Okay, so you can find it from this particular you can say information or the test results of this. Okay, and it is like whenever you will contact a particular fabrication lab, they will provide you these details, that what is the minimum VTH, what is the maximum VTH, what will be the W by L ratios, okay, what will be the mu and cox values. So these values actually you can get it from MOSIS website, or you can contact the particular fabrication team and they can tell you. Okay, so from there you can get all this, and you can also look into the model files also somewhere. Sometimes it is written in the model files also, or you can collect these particular acceptance test results. So there you will get it. So I hope like you have learned this. The differential amplifier that I have shown today, actually we have considered the mu and cox value. Okay, so mobility we have just assumed. Okay, so that mobility value we have not calculated the exact value of the mobility. So that's why we are getting a different result in our case. Okay, so we are getting a different result because we have not considered the actual mobility, that is a Kp value or Kn value. So because of that only we are getting a different one. But if we consider the mobility value, okay, so if we are considering the mobility value, that is the actual value for that particular technology file, then we'll get the you can say the exact value. Okay, so we'll get the exact value for the, and when we'll do the simulation, so we'll get we can match it with our specifications. So when we will match it with our specifications, so it will match to that. So I hope this is clear to everyone, how we do the simulations, how we can find out the parameters, and how we can know what is the VTH values, or what is the mu and cox values, then what is the minimum length width, or what is the maximum length width, and also like how we can know the parasitics of a particular transistor, and how we can do a Monte Carlo analysis. So these things today I covered. So if you have any queries regarding this, you can let me know.
Hello, sir.
Yes, Pranav.
Yeah, in the schematic, in the fourth comment, you
Okay.
considered the bias current as 100 microamp in the
Yes,
left
yes.
branch.
Okay, so let me get
Uh,
back to this one. Okay. Yeah, bias current I have taken as 100 microamperes. Yes.
yeah, in the fourth comment towards the right side, you
Okay.
have taken it as 100 microamp. Shouldn't it be 50 microamp, sir?
Okay, I bias. Here actually it is I'm taking 0.5. So on my right hand side it is 0.5. Okay, and here on my left it is also 0.5 multiplied with this Kp value and this whole value, right?
Okay.
Because the ID current, that is the current through this particular transistor, it is half mu and cox W by L VGS minus VTH whole square. So for that one, so this 0.2 and this 0.2 will get cancelled out because I3 is equal to half of I5. Okay, so that is why I have written like this, and I have cancelled out this 0.5 and 0.5.
Okay, sir. Thank you. Understood.
Okay, okay, okay. So is there any other query?
Okay, we can stop for today, I think.
Okay, sir. So tomorrow we can start with the op-amp designing, and we can continue with that one.
Okay, thank you.
Okay, thank you, Apurva, sir. So I'll be disconnecting now.